Hi, we've been discussing the electrical circuit. Now let's talk about the work done and the power generated in an electric circuit. But before we do that, let us take a few steps back and remind ourselves of some definitions and formulas that will help us in understanding the work done and the power in an electric circuit. So let us start with current. Current I is the rate of electrons or charges moving through the system. Or in other words, we can also say it is the amount of charge Q per unit time t as presented in this equation. Now current, we know, is measured in amperes. We can also say that the total charge Q at a point on this conductor is the product of the current that passes through that point and the time it took to pass. This charge is measured in coulombs. One coulomb is the quantity of charge which passes any point in a circuit when 1 ampere of current passes through in 1 second. Now we know that force is what we need to do some work, right? Force in an electric circuit is the energy applied to the charge. And the force that moves these charges through the circuit is called electromotive force. Now this has the same value as potential difference and is also measured in volts, V. So now, when that potential difference moves a charge from one point to another, we say work has been done, right? If the potential difference V is applied on a charge Q, then work done is V times Q. Recall that the work done is in joules, which is the product of the unit of Q, coulomb, and the unit of potential difference, which is volts. Remember also that we just said that the total charge Q is equal to current I times T. Now if we place this into our equation for work, we have work is equal to V times I times T, which gives us our first equation for work done in an electrical circuit. Now recall from Ohm's law that V is also equal to I times R. So work done can also be expressed as work is equal to I squared times R times T. Also remember that Ohm's law can be represented as I is equal to V over R. So this work done can also be written as work is equal to V squared times T divided by R. Now work done can be used to convert electrical energy to heat energy, like in electric kettles or in room heaters. The amount of heat released in joules is equal to work done. Power, we have learned earlier in a previous quest, is the rate of work done, or work done per unit time. The SI unit of power is watts, where 1 watt is equal to 1 joule of work done per second. So to find power easily, we divide all three equations for work by time t, which leads us to power is equal to V times I, or power is equal to I squared times R, or power is equal to V squared divided by R, as you can see on your screen. So how can this be applied to our daily lives? You would notice that most electric appliances usually have markings on them, like say for example 250 watts, 220 volts. An appliance bearing this mark means that when it's connected to a circuit that has a potential difference of 220 volts, it consumes a power value of 250 watts or 250 joules every second. These markings are usually referred to as ratings. This also implies that the current required to run this application can be gotten from the relation P is equal to V times I. Now substituting our figures for power and voltage from the ratings and solving for current, we have I is equal to 250 divided by 220, which is equal to 1.14 amperes. So what did we learn in this lesson? In this lesson, we expanded on our understanding of work and power as it applies to an electric circuit. In the next lessons, we will see further applications of these principles. See you all there.